Okay, everybody. So today I'm going to go ahead and finish off Kepler's second law, and I'm just going to have you guys watch this video. Hopefully you can sit back and just kind of relax and enjoy, I guess, the lecture of it all. Okay. So if you remember what we were trying to do is we're actually trying to figure out Kepler's second law, which states as a planet moves through space, there's going to end up being, it's going to sweep out equal areas in equal amounts of time. Okay, so so if we have like some sort of a picture, okay, so just kind of drop a picture, and I'm going to draw this kind of awkwardly on purpose because I know where we're going with this. So just kind of go with me here. Okay, so what I'm going to do is I'm going to represent this on an XY plane, but the XY plane is going to be viewed from an angle. Okay, so this is going to be at 90-degree angle right there. Okay, so what I have, and what I'm going to do is I'm going to deal with this as my sun. Remember, that's going to be one of the points, one of the foci of the ellipse that it travels, and then the path of the object is going to go something like this. Okay, so it's going to travel like this, and it's going to go around. So what our goal is then is our goal is to somehow calculate what this area is. So I'm going to call this theta. I'm going to figure out what this area is, and as it sweeps along, as it goes in this direction right here, it's going to be sweeping out equal areas in equal amounts of time. Okay, so that's what the goal is. That's what we're going to be doing here. Okay, I'm going to kind of bounce around all over on the paper because I think it's better explained that way. Instead of just going straight through, I'm going to like hit on key points and focus on the key points and then the motivation to getting those other points. Okay, so let's go back. So remember what we're going to do is we're going to switch this to polar and we're going to sweep out the area. So how do you sweep out the area? Now the formula is already there. Okay, and the formula that we had last year for polar was area was equal to the integral of 1/2 r squared d theta. Okay, so that's what the formula was. So right here, all we're doing is we're just simply rewriting this. And we're rewriting this instead of r, we're going to represent it as an f, and f of some phi, which is just some angle measurement. This is a temporary placeholder variable because in a second we're going to use the second fundamental theorem of calculus. We're going to plug in theta and theta naught, and we're going to plug it in there to get our values. Okay, so what do we have then? We have some arbitrary value theta naught, and we want to rotate it through to figure out what that's going to be. Okay. So we have this equation, but like I said, I'm going to write it in terms of phi. And now when I take the derivative of both sides, I have to apply the second fundamental theorem. So ignore this in a moment. Okay, ignore that. So I have, just going over here, I have dA dt is going to be equal to 1/2 f of theta squared d theta dt. Okay, so I take the derivative of both sides here with respect to t. Okay, and by the second fundamental theorem, remember what you do is you plug in the top and then you multiply it by its derivative. Well, that's what I did. I plugged it in and I multiplied it by its derivative. Minus, right, because you have to subtract off, so you plug in the bottom right there, and then you multiply by the derivative of theta naught. But the key there is the derivative of theta naught is 0. So the second portion goes away. And so I'm just left with this. So that's where this comes from right here. And then all I did is instead of f of theta, I plugged in r squared because r is the same thing as f in the terms of this problem. Okay, now don't worry about the rest of it though, like this portion and this portion right now. Don't worry about that. We'll get to that explanation in a minute. Okay, so once again, what are we doing? We're sweeping out the area to come up with what the area is. And my goal is if it sweeps out equal areas in equal amounts of times, that means when I take the derivative with respect to t, this should be a constant. That's what I know. Okay, so right now, here's where I'm sitting. I knew what the area equation was. I took the derivative, so I end up with this equation right here. And my goal is to show it's a constant. Okay, that's what my goal is. Okay, so how are we going to do this? Well, one half is obviously constant, but what about r squared and d theta dt? So I guess when I do this with d theta dt, the key to doing this is to figuring out like what is the relationship of theta with respect to time. Can I somehow manipulate the system, the equation that I have, to have this be d theta dt? Okay, so let's go back and let's actually set this up. Okay, so once again, if I go over here and I have this picture, so what I'm going to do is I'm going to like introduce a coordinate system. We're going to set it up so we have something to work off of. Okay, so we're going to introduce a coordinate system. Okay, so the first thing is the distance r from well, let me write this down and then we're going to have to switch directions here. From M to M is minimum at t is equal to 0. Okay, so what is the M and the M? Okay, so last week we actually talked about this right before we left, and we came up with this, Newton's law of universal gravitation. Okay, so we had some sort of relationship here. M is the little mass, M is the big mass, R is the distance, G is the gravitational constant, and F is the magnitude of the force. Okay, so this is the relationship that we had last week. And so what we're going to do is we're going to utilize that to come up with some sort of an equation that's going to have a theta inside of there. Okay. So we're going to have some sort of a mass right here, which would be the smaller object. This would be like M, and now over here would be the bigger one, which is the sun. Okay, so that's the first part. Okay, the second part is the mass. Oh, and so I'm sorry. So the distance r is the distance from there to there. So that's like a vector. Okay, as it gets swept out in that direction, that r is going to change. Okay, so the second one is the mass m has a non-zero position and velocity vectors r naught and v naught at t is equal to 0. Okay, so that's what we know. Okay, the next thing. Okay, so a polar coordinate, because once again we're going to work with polar. System is introduced with its pole at mass m. So once again, that's where the big M is going to be. So right there. And then that's where little m is going to be. And oriented so theta is equal to 0 at t is equal to 0. Okay, so basically when we start, the way we're setting this up, when we start, the lower mass or the planet is going to be right there, which will be on the, if you will, the x-axis. And I call that the y-axis. Okay, and then the last portion is the vector v naught is perpendicular to the polar axis at t is equal to 0. Now, I should actually go back and restate this. We're going to kind of have like two different coordinate systems on top of each other. This is x and y, but we're actually in the polar system, so there's no such thing as x and y. But I'm going to basically like superimpose them on top of each other. Okay? So this is the x-axis, but this is also the polar axis right there. And so what this is stating is that time is equal to 0. The velocity vector is perpendicular to polar axis. So it's going to also be going that direction like that, where that's 90 degrees. Once again, view this from like, we're viewing it from like above and from an angle. And once again, you'll understand why later. Okay. So that's the system that we're going to be working in. Okay, now let's go back up and let's talk a little bit. Let's like zoom in right here to what this R is. Okay, let's zoom in there. So when I zoom in, my picture kind of turns into this. So we have this R vector, which is the position vector. And one of the principles of physics is each action has an equal and opposite reaction. So basically the forces that they're exerting on each other are the same. Okay. So if this is F, this is going to end up being negative F. So I'm going to rewrite this a little bit. And once again, you're not going to really see why for a little while. It will come into be later on. Okay. So what I know then is if R is this, then I know the magnitude of R. Is the distance between M and lower M. Okay, so what I'm going to do now is I'm going to write F, but I'm going to write it in terms of R. Okay. So what I know then is the force F is equal to, well, the magnitude of the force F. Okay, because so that tells you how big it is, but if this is a vector, I need to give it a direction. So R is the vector that's going in this direction, but F is the one that's opposite or acting in the opposite direction. So what I'm going to do is I'm going to say, well, this is the magnitude of F times negative R all over the magnitude of R. Okay, so if you think about what's happening here, the negative is going to make the vector go in the opposite direction. When I divide by the magnitude of it, it turns it into a unit vector. So it's a length of 1. So this right here has a length of 1, and I don't know, maybe that's only like this little portion there. But if I want it to be the vector F, then what I'm going to do is I'm going to take that direction which it's going, and I'm simply going to multiply it by how big that capital F is. Okay, so that's all I'm going to do. Okay, now because I don't like writing all of these double bars, I'm going to let the magnitude of R, and this probably will actually make it more confusing for you, sorry, as R tilde. Okay, just a little bit easier to write. So then we have F is equal to the magnitude of F, times negative R over R tilde. Okay, so now what I'm going to do is I'm going to go back to Newton's law of gravitation, universal gravitation, right here. And I'm going to rewrite that okay, sorry about that. I just had to quick because my memory was getting low and it was going to stop on me. Okay, so anyway, so what I'm going to do is I'm going to take this and I'm going to rewrite this equation, but I'm going to rewrite it in terms of this. Okay, and this is r tilde. Okay, so if you notice, this has a magnitude of f. This has a magnitude of f. So I'm going to solve for the magnitude of f here. So magnitude of f is equal to f negative f times r tilde all over r. Okay, so then I'm going to place it in for this equation up here. Okay, and in doing so let me just write it in there right there. I'll do the work right here. So I have negative f times r tilde all over r is equal to g m m all over r squared. And then I'm going to solve for f. So in solving for f, I get f is equal to negative, and so I have to go back here real quick, and I have to talk about what this r is. R right here is the distance from each other. So in other words, this is an r, but it's really an r tilde. Okay, so this right here is an r tilde. So then multiplying this up, dividing that down, I have f is equal to negative g m m all over r tilde cube times r. Okay, I know that seems more complicated, but that's what we're going to use. Okay, so I'm going to go ahead and write this on the opposite page then. So therefore we have f is equal to negative g m m all over r tilde cubed times r. But I also know that force is equal to m times a, mass times acceleration. So I know F, which is equal to ma, is equal to negative g m m all over r tilde cubed times r. And I can get rid of one of those. So I end up having a is equal to negative g m m all over r tilde cubed. Okay, I know this doesn't make any sense, and this doesn't seem like it's helping out at all. We'll get there. Okay, so let's just go back and rehash what we were doing. Okay, so if you go back to the original, you can see, or if you recall, what we're trying to do is we're trying to actually come up with an equation for this. Okay, we're trying to show that this is constant. And so in doing so, I got this equation, and I need to show that r squared d theta dt is a constant. If I can do that, then the rate of change of the area with respect to time is going to be constant, and I'm good. Okay, so then what did I do? We went and we set up some sort of a coordinate system, and now we're using this coordinate system, and using this coordinate system and Newton's law of universal gravitational, we came up with this. Okay, so now what? Okay, so the problem is it doesn't really seem like we're going anywhere with this, right? Like, how do I bring in theta? Because I have this equation, I have d theta dt, and I have this equation, but I'm having a hard time understanding like where the constant portion is going to come into play. So this is the genius part in this. Okay, so what they did here is they said, okay, I'm having a hard time showing that this is actually going to be a constant. So what I'm going to do instead is I'm going to look at it, instead of in 2 dimensions, I'm going to look at it in terms of 3 dimensions. Okay, so that is why, remember a second ago when I drew in this picture and I drew it slanted like this, the reason why I drew this in is because now what we're going to do is we're going to look at this picture, but instead of looking in the picture in just 2 dimension, we're going to look at this picture in 3 dimension. So this is the z-axis. And then what I'm going to have here is, so I know that r naught is going to be this vector right here. And this vector right here is going to be v naught. And what I know is I know that when I take r naught and cross it with v naught, I should get some vector that's perpendicular to it. That's the definition of cross product. So you're going to get some vector, and I'm going to call that vector b. So this vector, when I cross it, is going to be that vector right there. Now, what's really nice about this, and this is the key to doing all this, this is the crux of it all. I know that since v naught and r naught are vectors in that plane, and when I cross them, I get b. Well, r naught and v naught are constants. And what that means is when I take any two vectors in the plane, and I'm going to call those any r and v, it's always going to be equal to b, because that's the definition of it. That's how we actually came up with it. Okay, so I'm going to take these two, I'm going to cross it, I'm going to get a vector b. Okay, so going back to what we were doing before, right here, remember what we're saying is I have this equation right here, and this equation is in terms of theta, which is not necessarily a constant, but what we're going to show is we're going to show that when we take r squared times d theta dt, that will give me a constant. And right here, this is going to be the bridge between the two, right? These are both equal to b, which is a constant. This is a constant, and I'm going to show that that is going to end up being tied into that constant. So that's like the bridge. We don't necessarily, like this, these are in terms of some arbitrary values t, but it turns out that those are going to be constants, and that's going to be the key to everything. Okay, so let's go back and let's go to this side. And so we're going to let the magnitude of r naught be equal to r tilde naught, and we're going to let the magnitude of v naught be equal to v naught tilde. Okay, and so then what I know is I know that r naught is going to be equal to r tilde naught times I. We'll go over that in a second. And I know v naught is going to be equal to v naught tilde times j. Okay, so think about what this is doing. You remember, I is the vector 1, 0, and since we're in 3 dimensions, it's going to be 0 there. And j is the vector 0, 1, 0, like that. So if you go back to the picture, this vector, all I'm doing is I'm simply rewriting it in terms of I and j, and I'm saying, well, it's equal to the magnitude of r naught. Oops, sorry, you can't see that. It's equal to the magnitude of r times I, which is going in that direction. So that will give me that same vector. Okay, so what do I know then? I know that b, which is equal to r naught crossed with v naught, that was the definition that I gave you on the other side, is going to be equal to, making these substitutions, r naught I crossed with r naught tilde I crossed with v naught tilde j, which is equal to r naught tilde v naught tilde k. Okay, why did that work out that way? Okay, so right here, if you notice what we're doing, we have two vectors and we're crossing them with each other. Okay. So what is this vector? That's going to be, once again, you have I, j, and k on the top. This row right here, so you're having this vector, which is only r naught tilde, and you have 0, 0. And then this vector is only 0, v naught tilde 0. And so when I take the determinant, basically everything cancels out. The only thing you're left with is k times this minus 0, which gives us this. Okay, and if you look, you cheat a little bit, and you go down to what we're trying to do, notice there's the R naught V naught, which is a constant. Okay, so once again, we're trying to turn this into a constant. This is a constant, so somewhere it's going to come into play with this. Okay, also, I'm going to let u be equal to cosine of theta I plus sine of theta j be a unit vector where you have r is equal to r tilde cosine of theta I plus r tilde sine of theta j. Okay, now why is that important? Okay, so first off, why does it work? This is cosine, by the way. Why does it work? Cosine of theta and sine of theta, that's just going to basically travel around would be the unit circle. But r of tilde is going to end up changing as you go along because that's the magnitude of it. So it will map that out, right? So this right here is going to just give you the direction in which you're going. So if you think about the unit circle, it's going to give you the direction in which it's going. But as you move along, you're going to multiply by r tilde, which is the magnitude. So that's going to change where it's at. So instead of it just going around in a circle like this, maybe it's going to go in an elliptical path, more like that. So this is equal to r tilde times cosine of theta I plus sine of theta j, which I could rewrite then as r tilde u, because that's what u is equal to. So if r is equal to r tilde u. And the other part that's nice about this is it brings in theta. Remember what I'm trying to do is I'm trying to get this d theta dt thing here. Okay. So where do we go from here? Is there another equation that we have that has an r and an r tilde to it? And the answer is yes. Okay, if you go back to the equation that we had before right here, there is an equation that had r and r tilde in it. Which, if you recall, we reduced to this. I'm missing an r here. You guys probably noticed that earlier why I dropped the r, sorry. Okay, so there's an r and an r tilde. So I'm going to call this equation 1. Okay, so plugging this into equation 1, we get A is equal to negative GM over R tilde squared times U. Okay, but what else do we have? Okay, so we have A, which is acceleration, and U, which is this thing right here. So I also have this. I know V is going to be equal to dr dt. That's just the definition of velocity, which in turn is equal to d dt of r tilde u. By that substitution right there. Okay, instead of r, I have r tilde u. Well, using the product rule, then this is going to be equal to r tilde du dt plus dr tilde dt u. I'm going to end up running out of room here. But we also know, I'm just kind of breaking it here because I'm going to run out of room. I didn't plan accordingly. I also know that B, which is equal to R crossed with V, right? The position with the velocity, is therefore equal to R tilde U, because that's what R is, crossed with V. But what did I just show V was equal to? V was equal to that. So this is this crossed with R tilde du dt plus dr tilde dt u. Okay, so what do we got here now? We have a vector crossed with another vector, because that's really what that is. And so if you remember, we basically just distribute the cross product. And that was one of the earlier properties that we learned. Okay, so in doing so, I'm going to take this cross with this. So you have R tilde. R tilde. R tilde is a constant. So this is just R tilde squared. So when I do this, I'm going to have R tilde squared. And then I'm crossed with U crossed with du dt. Okay, plus, and then I have to take this crossed with that. So I have a u and a u. And then these are going to be the constants, dr tilde, t, and r tilde. So I have r tilde, dr tilde, dt, and then u crossed with u. Okay, I have u crossed with u. But u crossed with u, hopefully you remember, is equal to 0. This is equal to 0. So then this turns out to be equal to r tilde squared u crossed with du dt. Okay. So if you look, remember what I'm trying to, and by the way, like, what is this equal to? Follow it back. Okay, it's equal to this, which is equal to this, which is equal to this, which is equal to b. Remember, b was a constant. So I did know that that was equal to b. Or, if you will, r crossed with v. Okay, what is du dt then? So let's take a closer look at this. So I'm going to go right here. I'm just going to have to try and write small. So I have du dt is equal to, so I'm going to take the derivative of this thing with respect to t, which means I need to use the chain rule. So this is going to be du d theta, there it is, times d theta dt. Remember what I needed? I needed d theta dt. I needed that. And here, there it is. So let's go forward and let's actually figure out what this is equal to. So this is equal to the derivative of u with respect to theta. So the derivative of u with respect to theta, so this is just negative sine I plus cosine theta j. So negative cosine theta I plus, I did that wrong, sine theta I plus cosine theta j. And then it's still dotted by d theta dt, or multiply. Now, why did I do that? Because I wanted to know what this was equal to, du dt. And the reason why I wanted to know what that was equal to is because I want to go up here and I want to cross it with this. So let's take u, and I'm going to cross it with du dt. Well, that is just this vector crossed with u. which turns out to be just d theta dt k. Now, I'm going to leave that. If you guys want to go and do that yourself, you guys can go and do that yourself. But it's not really that complicated, because if you're going to take the vector u, which is cosine theta plus sine theta, and you're going to cross that with du d theta, which is this. So if you think about what's going to happen there is you're going to have ijk in the top. You're going to have cosine sine in the next row. Let's actually write it up here. I'm not going to do this out, but ijk, and then you have cosine theta sine theta 0, and then you have negative sine theta cosine theta 0. You do have a d theta dt in there, right? There's a d theta dt in there, but I'm going to ignore that for the moment. So right here, when you go through and take the cross product, you're going to have cosine squared plus sine squared, which is going to give you the 1. Cosine squared times cosine squared minus sine times sine. So that's going to turn into 1, and this is all you're going to be left with right here. Okay, d theta dtk. Okay, so that is what this is equal to. Okay, so what do we have then? We have b is equal to r tilde squared times d theta dt k. But I also had another equation for b. And where was it? Actually, no, that's it, right? Because look what I'm trying to do. There is the r tilde squared d theta dt, which is right here. Oops, sorry. Actually, no, we do know that b was equal to r naught v naught times k, right? Okay, we did know that that was true. This is one of the first things we figured out. So because of that, you know that this portion is equal to that portion. Okay, so coming down here, like I said before, we have r squared d theta dt, which is r tilde squared. Remember, r is the length of it, so we're fine here. R squared d theta dt is equal to this. So just simply substituting in what this is equal to, I have 1/2 r naught v naught, and this is a constant. And since this is a constant, the rate of which the acceleration is changing with respect to t is a constant. And I've just proven Kepler's second law of planetary motion. Okay. I don't know how easy that was to follow online as I'm going through this and you're not able to ask questions. I apologize for that. I kind of feel like the people that want to listen to this are going to go back and listen to this. I think it's kind of cool if you can follow it all through. And the people who would check out and are like, I'm not going to really listen to it, well, they're not going to listen to this. So anyway, I just thought it'd be a good thing to do is just post this video, have you guys go through and watch it, and then we'll start on Unit 2 tomorrow. Tomorrow. Okay? So there is Kepler's second law of planetary motion. Hopefully you enjoyed this. I know it was like all over the place and piecing it together. It does get easier from here. I'll be honest, this first unit was kind of a lot, especially towards the end here. So I look forward to working through the rest of the units with you guys. Okay, thanks everybody, and we'll see you tomorrow.